Okay, then I'm going to present you. Today, I have a unit root theoretical distributions and unit root test. If you have any questions, please interrupt me. Okay, are you able to see the slides?
Yes, sir.
Okay, I'm going through. Today, as I said to you, I'm going to offer you the distributions. We have T distributions, normal distributions, and we will then go then after the unit root, the theoretical interpretations, and next week then I will introduce you and do some estimations on the EU. As I said to you, the distributions, normal distributions, T distributions will be given to you today. And normal distributions is going to be evaluated and interpreted regarding to its properties and the formulas, and some calculations, small simplest calculations will be given to you. The main concept and the learning outcome here is to understand the reason of these distributions, the so-called the inverse belly-shaped figures, these standard deviations, and its impact to the unit root and the test that we are using in the regression analysis. The normal distribution, which is known as the Gaussian distribution, is probability distribution that is symmetric about the mean that we have done in the first lecture, showing that data near the mean are more frequent in occurrence than data far from the mean. In graphical form, the normal distribution appears as an inverse belly shape or belly curve, as I mentioned to you. You know, this is the standard deviations, which is the two tiles mostly accepted and used for these estimations in the unit root. The key takeaway here is the normal distribution is the proper term for the probability bell curve. The normal distribution, the mean is 0 and the standard deviation is assumed to be 1, and it has 0 skew, and the kurtosis is supposed to be 3. The normal distributions are symmetrical, but not all symmetrical distributions are normal. Many naturally occurred phenomena tend to approximate the normal distribution. In finance, most pricing distributions are not, however, perfectly normal. The normal distribution is the most common type of the distribution assumed in technical stock markets analysis and in other types of statistical analysis. The standard normal distribution has two parameters, the mean and the standard deviations that we have done, as I said in the first lecture, that it is introduced to you, and you probably know what is it and how it is going to be estimated and affect the your theory and your model. The normal distribution is important in statistics, and it is the key to the central limit theorem. This theory states that average calculated from independent, identically distributed random variables have approximately normal distributions, regardless of the type of the distributions from which the variables are sampled, provided it has finite variance. The properties of the normal distribution. The normal distribution has several key features and the properties that define it. The first, it is the mean, the average, so-called the median, the midpoint, and the mode, the most frequently repeated or observed number or article are all equal to one another. Moreover, these values all represent the peak or highest point of the distribution. The distribution falls symmetrically around the mean, the weight of which is defined by the standard deviation. The empirical rule here, the normal distribution is supposed to be around 68.2% of the observations will appear within plus or minus 1 standard deviation of the mean. And if the normal distribution observed 95% for of the observations will fall within plus or minus or minus 2 standard deviations, and 99% 7 within plus or minus 3 standard deviations. This fact is sometimes referred to as the empirical rule, a heuristic that describes where most of the data in a normal distribution will appear. We are going to illustrate on the graphic here. As you are observing here, the empirical rule, as it is mentioned in the theory, is illustrated on the graphic, and the 68% is around the mid of this peak, or so-called the belly shaped, which is divided to the minus and plus 34% for each, and for 95%, which is going to be divided again to the peak, is going to be 13 plus for each, and the 99% is going to be 2.1% for each, plus and minus is given. For an approximately normal data set, the values within 1 standard deviation of the mean account for 68% of the set, while within 2 standard deviations account for the 95%, and within 3 standard deviations account for 99%. 7 standard deviation shows the percentage around the theoretical probabilities intended only to approximate the empirical data derived from a normal population. It is again here illustrated. The 68% of values are within 1 standard deviation, or let's say the peak of mean value, and the 95% of all values are within the 2 standard deviations of the mean value, which is illustrated on the graphic above on the figure, and 99% of the values are within 3 standard deviations of the mean. As you are observing, it is distributed plus and minus to the equally, which is a normal and symmetric distribution is subjected here. The skewness measures the degree of symmetry of a distribution. The normal distribution is symmetric and has a skewness of 0. If the distribution of data set instead has a skewness less than 0 or negative skewness, left skewness, then the left tail of the distribution is longer than the right tail. The positive skewness, right skewness, implies that the right tail of the distribution is longer than the left tail. Therefore, skewness is also becoming very important in the standard deviation and the representation of the descriptive statistics and the impact to the model. As you are observing here, this left skewness, which is negative, and right skewness is positively represented here. On the left skewed, as you are observing, the mean, media, and mode is in the Q, and the right skewed or the positive skewness, it is then again mean, media, and mode is approaching to the belly shaped, which is right skewed and left skewed represented on these 2 figures. The kurtosis measures the thickness of the tail and of a distribution in relation to the tails of the distribution. The normal distribution has a kurtosis equal to 3.0, and the distributions with larger kurtosis greater than 3 point exhibits the tail data exceeding the tails of the normal distribution 5 or more standard deviations from the mean, and this exceeds kurtosis is known in statistically as the leptokursic fat tails, so-called. The occurrence of fat tails in financial markets describes what is known as tail risk. Distributions with low kurtosis less than 3 point play kurtosis exhibit tails that are generally less extreme, so-called skinner, than the tails of the normal distribution. The formula for this is then, of course, will give it to you in following. If the descriptive statistics estimated kurtosis value for all considered parameters are positive, which implies that the distribution has heavier tail and a sharper peak as you are observing on the graphic than normal distribution. Further in distribution where a negative kurtosis value is observed, the curve has lighter tails and a flatter peak, which is not illustrated here, but the first one is represented. A rounded curve than the normal distribution, which is not observed in this study, which is taken from my paper. In this figure 2 below is represented. This solid line indicates the normal distributions and the dotted line shows the positive kurtosis values. I hope you are understanding this up to now. The formula for the normal distribution is given here. The normal distribution follows the following formula. Note that only the values of the mean, so-called the P or mu, is represented, and the standard deviation is the let me check. This is sigma, and the normal distribution formula is given as its f is divided to f is equal to 1 over sigma root square 2p power of e 1 over 2 minus will be then x minus epsilon will be divided to the sigma, which is power of 2. The z-score and standard deviation relation. The z-score indicates how much a given value differs from the standard deviation. The z-score, so-called the z-score or standard score, is the number of standard deviations a given data point lies above or below mean. The standard deviation is essentially a reflection or the amount of the variability within a given data set. We are giving here a sample question or example. Let us consider use the normal distribution table and find the area, which I'm going to give you the table. You can find in the, let's say, Google this normal distribution tables, but I will give you now in the following slides. Use the standard formula, Z's formula, so-called, or Z-score formula is again x minus mu divided to sigma is the formula, and Z is the average percentage value, x is the normal random variable, and mu average mean value, and sigma is the standard deviation. And the example is given here, mu is 5 and the standard sigma is 2 in a normal distribution. Please find the deviation area between x is equal to 6 and x is equal to 9. Of course, for finding such questions, you have to find the given this area, this 6 and 9, and then you will then determine this from the table. Z is going to use again the formula. Z-score will be used, which is given here. 6 minus 5 divided 2 is 0.5, and for the 9s for the Z-score, 9 minus 5 divided 2 will be then 2, and then we will look standard normal distribution table for 0.5, and it is I'm going to show you this. This is here for 0.5, as you are observing for the 0.6915, as it is given here. Okay, and for the second one, for the 2, when we are looking again to the table, Z-score for the 2 on the very left side on the vertical line, the 2 is 0.9772. Did you see this table? Which is representing the standard deviations and the estimation for the normal distributions. Are you seeing this table?
Yes, I do see it.
Or you are familiar with these tables?
I am
Yes,
not familiar with it.
Okay. Fine. Are you seeing the figures now again?
Yes.
Okay, did you get these 2 and 0.5 figures on the second vertical line? For the 2 is 0.9772 and for the 0.5 is 0.6915, because this is taken from the midpoint. As you are seeing, this is a belly shaped, inverse belly shaped, and on the midpoint is 0.5, and after the 0.5 you are adding some points. Therefore, we have here for the 0.5 is 6915, also called 0.6915, and for the 2 is 0.9772. Okay, when we are going back to the example, then we are going to subtract these two numbers for illustrating the figure. Then you will get 0.2087, which this gives you the area between 6 and 9, and it is representing 28%, 57, which is illustrated here. As you are observing here, we are showing here this graphic. Okay. Here we are having the other example. As you are observing, again, mu is 5 and standard deviation is 2. Then when you are going to calculate for 1 and 3, then you will get, again, for 1 is -2 and for 3 is -1. Then you will get, again, find these numbers from this table. As you are observing here, 1 from the right side, 1 from the left side, which is going to be estimated after 5. As you are observing, this is started from 0, 0 is the, let's say, the central point is 0.5000. Then after then you are going to, because you are looking for the numbers here, sorry, here, 2, -2, and -1. And -2 is going to be then 1 is 0.8643. Then you're going to subtract it as you are observing here. Then you will get it 0.3413, which is going to be subtracted from the midpoints, so-called the belly shapes, centrals. 0.8413 will be subtracted from the 0.5. Then this will then gives you the left side, which is 0.3413. And for the other two, then you will get then the number from the graphic as you are looking to 0.9772. You got it in the second line, in the second vertical line. For the 2, Z number is 9772. Then I'm going to introduce you this because probably you are going to exercise this in the EView without knowing this, but you have to know the theoretical application, because in the exam, I will ask you such questions for being able to understand the standard deviation and why it is going to affect and change the model, isn't it? This is very important. Then we are going to subtract this also, as you are observing, 0.9772 will be subtracted again from the mid 0.5. Then this will then give you 0.4772. And when you are going to subtract these two numbers from each other, 0.4772 minus 0.3413 will give you then 0.1359, which is then the numbers between these two areas, so-called on the left side and on the right side. Then will gives you these standard deviations. Okay, then we are here assuming the weight of an orange. Now I'm going to give you another example, which is a little bit helping you to understand the reason why we are using this for the unit root analysis. Assuming the weight of an orange is 200 gram and the mean standard deviation is determined as 50 gram. What will be the percentage of oranges if the oranges 300 gram and above? Assuming the oranges have a normal distribution, sorry, and Z is again X minus mu divided to sigma, Here, then we're going to apply 300 minus 200 divided to 50. Then this will then gives you again set score 2. And for the x is then assumed to be 300. The area to the right is found by subtracting again from the midpoints, so-called in the graphic, you know, this 0.5. Then will give you then 0.4772. From half of the symmetric normal distribution, the area is 0.4772 if we subtract this from the 0.5, as I said to you, from the mid. This value is subtracted again from the total, which is 5, for getting the amount of this distribution. Then this is then again will be subtracted from 0.5. Then 0.5 minus 0.4772 or 0.5 minus 0.4772, then will give you then 0.0228, which is 2.28% of oranges are heavier than the 300 grams. So-called, and we are going to interpret and then present this simplest example in the let's say hypothesis and equation. Then how to develop and present these kind of applications will be illustrated here. Another question regarding to distribution of the weights of the oranges mentioned above is what value is the weight of 60% of the oranges below. As shown in the figure, we need to find the z value or z value in order to find the x value. Hypothesis generation. HO, the whole oranges is supposed to be 300 and plus, and H1, so-called the null and the alternative, the whole oranges is supposed to be 200 plus 50 for the given example. If the HO is in the acceptance zone, arithmetically, it is rejected if not accepted. And here, H1 is accepted because the arithmetic means is in the red region or is in the region, which means we are rejecting it. Sorry. Okay. T distribution. The T distribution is another form of these distributions. We have illustrated the normal distribution. Now we are jumping up to the T distribution. The T distribution is symmetrically distribution, and its appearance resemble a normal distribution. If the data is less than 30, the T distribution table is used. If the sample volume commands, the standard normal distribution table is used instead of T distribution, because the larger the sample volume, the closer the T distribution to the standard normal distribution. So it is a little bit somehow approaching to each other. Something happens, I think. I don't know. Let me check what is happening. I don't see my PowerPoints here. Let me see if something happens. This is interesting. Let me see if I have the PowerPoint somewhere else. I think something happens. I don't know what is happening, but I can open the PowerPoint. It's freezing, I think, or something happens. Forgot. Interesting. Sorry for this. I have to check what is happening, what's going on. I don't know, but I can. My screen is freezing.
Yes, so Jam, is it possible to make someone admin and then you log out and log in again?
I don't know what is happening, but it stopped. Let me check what we can do. I don't know why this has happened. Nothing. I think something happens and I can. Everything is strange. Interesting. I don't know, but nothing's happened. The nothing comes, nothing goes. It's interesting. I don't know what is happening. It's strange.
Maybe you can try to press the escape button, and then we can see what happens.
I don't know.
Okay.
But
So you still don't have the. Okay, maybe you can. Do you have the Windows button in the computer or the laptop? The Windows button.
Yes.
No. Yeah. Okay. Let's press that.
You want me to quit?
Yes, I think that's going to be the best. And then reopen the PowerPoint. But if it asks, to make any changes, you shouldn't click on yes.
I don't know why this has happened.
Normally what I do, I use the thing, CTRL Alt Delete, to see what tabs are open, close everything that is open, and then reopen the program.
Let me quit. Yes, okay. Check what we can do. Interesting. Let me quit this one. And again. Okay, it comes, I think, again. Let me check if I am able to. Okay, it's okay now. You are on now. Are you able to? Shall I have to share my screen again?
Yes.
I think now it is okay. Something happened. Sorry.
No, that's fine. You just need to share it again. That's it.
Okay. We were here, I think, isn't it? We were here. Where we were? We were here. Okay, I said this and then jump to the t distribution. As I said to you, the t distribution is a symmetrical distribution and it appears resemble a normal distribution. If the data is less than 30, the t distribution table is used. And if the sample volume commands the standard normal distribution table is used instead of the t distribution, because the larger the sample volume, the closer the t distribution to the normal or so-called the standard normal distribution. Okay. The t distribution formula is given here. Again, t is equal to x lambda minus mu. Probably you're coming and going, then something happens. And is going to divide it to the sample standard deviation to the root square of the n sample size. Okay, we don't use these formulas because we are going to employ the EView, but you have to know the theoretical application just in case what is happening, and you have to know the logic, how this is affecting and changing the model. Therefore, we are going to learn, we are going through these theoretical applications. The example here is given to you again for simplest one. N is 15. Let's find the value of T, which represents the 40% of the T area for the T is 0. In the normal distribution table, when we subtract the value of 0.4, which means 40% from the value of 0.5 from the, as you are knowing from the belly shape, then this will then gives you 0.10, which is the 10%. Half of the total area. For the area of the 40% in question, we will obtain the value of the T, which is given according to the value of the 0.5, for so-called the 10%, and the standard deviation. We will find again the intersection of the N minus 1, which is 15 minus 1 is 14 line, and this will then illustrated and estimated from the table again, which is given here, as you are observing here. The 14 value is given for 0.10 is 1 when you are going to the 1, 2, 3, 4, 5, the 10%. Okay. For the 14, when you're going to intersect this each other, then you will find 1.341. You got it? Did you get it? Or am I right? 3.45, I think. Yes. Yes, 3.45. Did you get it? This is then how it is going to be estimated for those who are employing and applying these theoretical applications. And as I mentioned to you, this is somehow not used anymore. We are having this all in the EView, and these things are all estimated for us and giving us the best possible model and log selection. All will be done, standard deviation, everything will be estimated using this. But you have to know the logic. Here we are having again another one-tail t-test. Yes, please.
Will you ask this kind of question for the final examination?
Maybe the theoretical. I don't know. Maybe some simplest with estimation of these things, maybe, but I don't assume such a regression. You know, regression is a long process. Maybe we will see, because I have to do exam for you, and in the exam, since we are not able to use the laptop or computer, and it must be a written exam, some theoretical questions must be given to you, isn't it? Therefore, some theoretical estimations and theoretical calculations and introduction and presentations is expected. At least you have to know what is mean mode media and how it is affecting and changing the model, these things. Yes, please.
Hocam, to the portfolio, we can put our results. For example, if we are doing any test, let's say if we are doing unit root tests, we can take the printout of unit root results. So we can mark them. If you would like to ask questions from the computer, which is going to be, I think.
Well, don't concentrate, my dear İlker değil mi? Ali.
Ali, sir.
Ali. Sevgili Ali. Don't concentrate to the exam, okay? If you learn, I know this. If you because I will make the exam online also, so there is no need to worry about it. Don't concentrate your exams. If I am believing that you are qualified, you will definitely pass. You don't have to worry about and concentrate to the exam. You join the exams, you join the classes, do your assignments or exams online and everything, then you will see nothing will happen. If you don't come to class, if you don't do anything, of course I can help you. But if you are following everything, then you don't have to concentrate, because you are going to qualify for becoming doctor for this business, isn't it? You become the doctor of philosophy or business. Am I right? Therefore, I am not going to force you to learn everything, because you are not going to professor for econometrics. But you have to know the quantitative and qualitative part of these exams and these estimations. Am I right? Did you get any micro exam, micro course?
Yes, I did.
What managerial economics? Managerial? What did you get?
Microeconomics.
Microeconomics. When did you get it?
In my bachelor's, which was very long ago. Like
no, my dear. I'm asking you for the PhD program, not for the bachelor.
No, I didn't take it.
This is of course something else. Okay, then I will request to employ you
masters.
In masters.
Yes,
but you don't have to do this. You didn't do it here.
In masters, I did, but
Because-
not everybody did the masters in our school.
I know. That's why, because you have to do this micro together, then this will then help you to understand everything and combine. You understand? Because you have to combine everything, because you're going to be expert in business, I think, because you are all in business. Am I right? You are coming from the business department.
Yes.
You are doing business PhD. Am I right?
Yes.
And in business PhD, I think you have to do one more managerial or some microeconomic courses with all qualified estimations and theories. This will then help you to understand and employ these things, because econometry will be also in it. And don't worry, we will go through first this class, this course, and then we will see what will happen. Okay, you concentrate this and try to understand what we are introducing you. And next week I will introduce you the EView, I will introduce you the unit root, I will introduce you the OLS or ordinary least squares, estimations, everything. And then we will go to the panel steadily. Okay, don't worry. Just let me go through with this, because we have a limited time and I have to finish this. If you have any question, then don't worry, ask me after this, then we will discuss this later, okay? Okay, as I said to you, then this will then 24, and again, when you are looking to the table here, this will then gives you. Okay, I am using the pointer and it is again stopped. Okay, here the hints. Let's read the hints to see what we're going. We see our t-test is one-tailed, as you are observing. So we will choose the one-tailed row to map our alpha level. Next, we look for the alpha value along the above highlighted row. I'm going to upload these PowerPoints and videos also to you. Then you will read and watch and understand better, because these things I wrote especially for you, for being able to understand step by step what we are doing. Anyway, we look for the alpha value along the above highlighted row. Our alpha level for this example is 0.05. Let us map the same on the table. Once that is done, let us map the degrees of the freedom under the leftmost column of the table under the intersection of these two presents, use with the critical values we are looking for. Then you are going to look this degree of freedom, so-called the example. This is not working again. When you are looking to the table here, you see this table, the 0.10 and 0.05 is going to be used for the 24, then the intersection is going to give in to you 1.711. Did you get it? Okay, this was then the how it is estimated. Then we are coming to the third one, the chi-square, so-called the chi-square distributions, definitions, and example. The chi-square distribution is continuous probability distribution that is used in many hypothesis tests. And the shape of the chi-square distribution is determined by the parameter chi, so-called the degree of freedom that we have done. The graph below shows the example of the chi-square distributions with different values of the degrees of freedom, or k, so-called. The degree of freedom, often abbreviated as DF or D, tell you how many numbers in your grid are actually independent. For a chi-square grid, as you are observing, given here many. For a chi-square grid, the degree of freedom can be said to be the number of cells you need to fill in before. Given the totals in the margins, you can fill in the rest of the grids using a formula. So this is, of course, not necessarily, but this is only given to you to see how it is affecting and changing the model, because this is also important. Let's see what is chi-square distribution. The chi-square distributions are a family of continuous probability distributions They are widely used in hypothesis tests, including the chi-square goodness of fit test and the chi-square test of independence. The shape of the chi-square distribution is determined by the parameter chi, which represents the degree of freedom. Very few real-world observations follow chi-square distribution. The main purpose of the chi-square distributions is hypothesis testing, not describing real-world distributions, unfortunately. In contrast, most other widely used distributions like normal distributions or Poisson distributions can describe useful things such as newborns, birth weight, or disease cases per year, respectively. The relationship to the standard normal distribution, the chi-square distribution, let me change this because it's not working. Okay. The chi-square distribution are useful, now is okay. Yes. Okay, chi-square distribution, imagine taking a random sample of a standard normal distribution as called Z. If you squared all the values in the sample, you would have this chi-square distribution with k is equal to 1, so-called x square is equal to z square. The normal, imagine taking samples from two standard normal distributions, Z1 and Z2. If each time you sampled a pair of values, you squared them and added them together, you would have the chi-square distribution with chi is equal to 2. Let me check if it is recorded because, okay, it's going to. You are able to watch these PowerPoints presentations? You following the PowerPoints?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Chi-square, more generally, if you sample, because there is a problem today with my laptop, if you sample from chi-independent standard normal distributions and then square and sum of the values, you will produce a chi-square distribution with chi degrees of freedom. And x square is equal to z square plus z1 square plus z2 square plus it goes like this to the n square or zk square. This is only the representation of the summations. We don't use this actually, but just in case to know what is it. And the chi-square tests are hypothesis tests with the test statistics that follows a chi-square distribution under the null hypothesis. Pearson's chi-square test was the first chi-square test to be discovered and is the most widely used. The Pearson's chi-square test statistics is x square, so-called summation or sigma, O minus E in bracket power of 2 divided to the E. In E is the expected frequency, and O is the observed frequency, and sigma is the summation of the operator, and x square is the chi-square test statistics. The chi is 1 or 2. The chi-square distribution is curve-shaped. As you are observing here, it goes inversely belly-shaped like a backwards J. As you are observing, the curve starts out high and then drops off to the somehow very low level, and that is the high probability, which is x square is close to 0. This is then the chi 1, if the chi is approaching 1. And when chi is greater than 2, the chi-square distribution, because you are going to use this chi-square values in the estimations, in the regression analysis, in the IRDL, in the vector error corrections, and you have to know why this is so important for your variables, because you are telling me that you are automatically learning these things and you are not understanding why this is affecting and changing your model. You have to know these things for being able to interpret your paper. You are understanding because you are finding some numbers, and if you don't able to combine with your parameters and interpret it, your estimation is nothing. You are not going to be evaluated or tested for the mathematics. And mostly this is done by the operator, EVU, or the strata. Therefore, you have to learn first this theoretical approach. Anyway, when key is greater than 2, the chi-square distribution is hump-shaped. As you are going to use a little bit up and down somehow, the curve starts out low, increase, and then decrease again. There is a low probability x square is very close to or very far from the 0. The most probable values is of x square, x or x square minus 2. As it is represented here, it goes up somehow to the probability approaching to 0.2 to 25. Then this is then key 3 or key also degree of freedom is 3. Then it goes again, so belly shape to the left, strongly skewed or so-called the belly shape directed to the right side. And here, as key increases, the distribution looks more and more similar to a normal distribution, as you are observing here. Now the key or degree of freedom is 90% and or greater. The normal distribution is good approximation of the Q-square distribution. When you are looking here, it is going 0.03 somehow, then it is increasing, similarly, parallelly, symmetric and distributed, and decreased again to the similarly and parallelly to the same direction. The properties for the Q-square distribution. The Q-square distribution starts at 0 and continues to infinity. The Q-square distribution starts at 0 because it describes the sum of the squared random variables, and this Q-squared number can be negative. The mean or so-called mu of the Q-square distribution is the degrees of freedom, and the Q-square distribution is right skewed, and the mean is greater than the media and the mode. The variance of the Q-square distribution is 2k. Okay, we are coming to the unit root. I think you know you are a little bit more familiar with this unit root analysis, but we are not going to do this. We are going to introduce you this analysis again, why it is done and what is the impact to the model. As you know, the unit root analysis mostly done before starting your application, isn't it? Therefore, every parameter will be tested. And when you are testing this, then this will then gives you whether you are going to use the I0 or I1 or it is mixed. And if it is I0, you are probably using the regression analysis. If it is I1, you may use the vector error correction or some others. Or if it is mixed, then you are going to use ARDL, autoregressive distribution somehow. Therefore, unit root analysis is very important. It is helping hand for you to testing the variables which is in the model, which is your model you develop, and then you are going to determine the explanatory and the dependent variables impact to the considered, let's say, study. Anyway, unit root test is a time series is not stationary or consistent of a unit root in a time series. Analysis is going to be subjected. The presence of the unit root in time series defines the null hypothesis, and the alternative hypothesis defines time series as stationary, that we desire, that we always prefer, isn't it? If it is rejected, the null hypothesis and the alternative accepted, then this is good for us, good for you. Then you so-called parameters becoming stationary, and then you can go further. Mathematically, the unit root test can be represented as y is equal to dt plus zt plus et, where the dt is the deterministic component, zt is the stochastic component, and et is the stationary error process. The unit root test basic concept is to determine whether the zt stochastic component for estimating speed impact of parameters, so-called, consists of a unit root or not, is going to be questioned. And in the unit root, it is an econometric approach that tests whether the mean and variance change over time, taking into account the autoregressive structure of the time series And as you know, the autoregressive models, as the name suggests, are models that returns to themselves. And that is the dependent variable and the explanatory variable are the same, except that the dependent variable will be at a level, at a later time, so-called, t level, and the independent variable is at the former period, so-called the t-1. Therefore, it is somehow expected in the same, but it is in the different period of time. We say chronologically ordered because we are now at time t. If we go forward one period, we go to t+1, and if we go back one period, we go to the t-1. Therefore, as I said to you, either you go one period before or to the further, then this will then expected to get some same impact or similarities on the estimated parameters, which is also important for the autoregressive. What is unit root? Unit root is also called root process or difference stationary process, which is going to take the difference, isn't it? Differentiated, the mathematical, you know, if you're going to get the differentiation of the one parameter, you're going to reduce it one. Is a stochastic process trend in a time series, sometimes called random walk with drift. Random walk, as you know, is always used in the economy. Then you are expecting to determine the impact of the some parameters on the certain parameters. If a time series has a unit root, it shows the systematic pattern that is unpredictable. So called here, it is a given an increasing linear curve, so-called the possible unit root. The red line shows the drop in output and path of recovery if the time series has a unit root, and the blue shows the recovery if there is a unit root and the series is then trend stationary. As it is observing, it is a line which is increasing direction. The unit root is the probability theory and the statistic. A unit root is a feature of the some stochastic process, variable or process that has uncertainty such as random walks that can cause problems in statistical inference involving time series models. A linear stochastic process has a unit root if one is a root of the process's characteristic equation. Such a process is non-stationary but does not always have a trend. If the other roots of the characteristic equation lie inside the unit circle, that is, have a modulus absolute value less than 1, then the first difference of the process will be stationary. Otherwise, the process will need to be differenced, because if it is not stationary, you have to do it, isn't it? We will do this also in the EView. Otherwise, you are going to employ it and you do by yourself, which is very difficult. You are going to only make some equations, simplest equations, and you will get the first difference of the data. Then you employ the unit root. The process will need then to be difference multiple times to become stationary. Usually, the first difference always satisfying. You don't need to get the second difference, which is not necessarily required, and no test required such application. If there are d unit roots, the process will have to be difference d times in order to make it stationary. Due to these characteristics, unit root processes are called difference stationarity. In statistics, a unit root test whether a time series variable is non-stationary using an autoregressive model. A well-known test that is valid in large samples is the Digi-Fuller test, also called the augmented Digi-Fuller test. A test for determining whether the mean variance and covariance of a time series are independent of the time is going to be estimated. And the unit root is a unit of measurement to determine how much stationarity a time series model has. Also called a unit root process, we determine the stochastic of the model using statistical hypothesis testing. the stochasticity process involving a randomly determined sequence of observations. As you are understanding, this is a process of determination the sequences in the observation. These are statistical hypothesis tests of stationarity that are designed for determining whether differencing is required. This is very important. If not, then you are not going to do, isn't it? If it is not stationary, you don't have to do your application. You don't have to go further. You have to make the data first stationary and then. In a model that has a unit root, of course, for some cases, as I said to you, there are some different applications, but generally you have to do either at level or at first difference. Then you make these estimations. In a model that has a unit root, why it is important, of course, we are asking. In a model that has a unit root, spikes and shocks to the model will happen is going to be estimated, and meaning that a shock stock price might make a big jump in the market, so-called, or big fall. That has nothing to do with seasonality, isn't it? This is very important. You are going to do this for making a reasonable estimation because you don't know what causes this effect. Some structural breaks may happens and cause this. Sometimes some changes may be when we are looking at the Turkish economy in 2000, where the Turkish lira was very depreciated. It was removed the 6.0, and then this was a very deep shock to the economy, bring down everything, somehow becomes a very stationary period. And now you're going to see in 2020 almost a similar scenario, because politicians always using such, let's say, applications. Of course, currently we are having some external impact to the economies, but this devaluation of the currency is also deliberately affecting and changing the market. And when you are making such estimation for the Turkish economy, you have to consider this structural base, because it is suddenly going up. As you know, in 2019 to 2021, 22, the Turkish lira very heavily devaluated and depreciated, and this will cause too much to the estimation when you are going to consider, for example, 2022, and the period will exercise some structural base, and you have to use some error terms for making some corrections. Probably it is not realistic. If not, if there is a stochasticity in the model, the effects of this shock, which is going to increase or decrease the value of the price, will disappear with time. If there is a stochasticity, it is so. But if it is not, then of course. An important thing to take it into consideration when building a broader business model is required. The unit roots that we are employing, usually we use Philip Perron, DG Fuller. I use usually these two mostly, and some Pesaran, but we mostly use this panel unit root test. Also is estimated for the panel data, and DG Fuller GLS test. I don't use Schmidt Phillips test, Philip Perron, as I said to you, and Zivot Andreu test are used, but mostly the DG Fuller is employed, and then Philip Perron is also for securing and for showing, and then Pesaran and some others are used. Elliott-Rothenberg Stokes test has two types. It is, of course, not going to be introduced to you. And the P test, so-called the panel unit test, that is based on the notion of median unbiased estimation that use the invariance property and the median function of the panel pooled OLS estimators that we use for the panel data, and takes the error terms for the serial correlation to account. And DF, so-called the DG Fuller GLS test, can be applied to deterrent data without intercept, and Schmidt-Phillips test subtypes are the row test and the tau test. The Phillips-Heron test is also supported and modification of the Digi-Fuller test, as I mentioned to you, and corrects for the autocorrelation and heteroscedasticity in the errors. And the Wood-Andrews test allows a break at an unknown point in the intercept of a linear trend. I don't use it actually. The Digi-Fuller test is a statistical hypothesis that measures the amount of the stochasticity in a time series model. The Digi-Fuller test is based on linear regression, and the Digi-Fuller test above actual creates a t statistic that is compared to predetermined critical values being below that critical statistics allow us to reject the null hypothesis and accept the alternative. And then you are going to process it. Then the unit root process is a data generating process whose first difference is stationary. In other words, a unit root process yt has the form y is equal to yt minus 1 plus the stationary process. A unit root test attempts to determine whether a given time series is consistent with a unit root process. And the next section will then introduce you the more detailed about the unit root process and they suggest why it is important to detect them. What does a unit root test do? In statistical, a unit root test, whether a time series variable is non-stationary and possesses a unit root, the null hypothesis is generally defined as the presence of a unit root, and the alternative hypothesis is either stationary trend, stationary or explosive root, depending on the test used. Modeling, I think if you want, I can stop here, then go through, because we have some 40 pages, 50 pages more. I think it is a little bit longer. You read this, and then we continue next lecture. Then I will do some presentations from the EView. Is that okay? Because if I'm going to give the others part of this presentation, this will then too much to you. Do you want me to stop here then? Because I don't know. If you want, I can go through. If not, then I can stop here. Tell me if you are okay, then I will go through.
You know better.
And you have to know if you are okay, you want me to go further, then okay. Then if you want to read this first part and the second part later, then I can do it. What is your opinion? Do you want me to go further, go through?
I believe we have been introduced to all the data, and we learned quite a lot for today. So we can just simply read the rest of it, and today we can stop at this point.
Okay, then next lecture I will go start from here and finish it, and then go to the EView to make the application for just only unit root, maybe some OLS also. I will do some regression analysis, but I think it will be fine. Is that okay?
Yes.
Okay,
Yes,
okay
sir.
then.
Yes, sir.
Okay, because I don't want to full up you with this too much because too many the definitions and theoretical explanations probably will come to you too much. Then we stop here, the modeling the unit root, and then we go next lecture through to finish it, and then jump up to the EView. And if you are getting, because I didn't get any feedback from you, you said that you already got this student version of this EView, isn't it? Did you all some students, did you receive this application or you didn't? Did you get the application?
No, I didn't.
Yes, I get.
Okay, you can share with each other. And this will then help you. I don't know, this Ahmet Öztürk is complaining we are not able to let him, but I requested him, but he didn't come. I don't know what is problem with him. Please contact Ahmet Öztürk Sakallı and ask him what is happening, because I don't know, he wants to attend to the class, but he is not able. He is still quitting himself. Let me know, okay, Hüseyin Ali Aker. Ask him what is happening. You are the assistant of the faculty. Is that possible?
I'll find out, hocam.
Okay. And the other, there is some other new students, new assistants. I didn't see them today also. Zilküf or what I don't know his name. They should also attend regularly to the class. this is a problem, you know, because I have to see their participation, and if they don't, then how I'm going to know what's going on? Okay, let them all give me the information. Next lecture, as I said to you, we will start some estimations. Okay, then we will see what will happen. And after the next week, I will let you to do some online. Okay, I will see you simplest estimations and applications. Then I will evaluate you out of 10% or maybe 20%. Okay, and then I will give you an quiz also. And at this quiz, this application also. This application will be added to your written exam also. You are understanding?
Yes, sir.
Okay.
Yes, sir.
Okay, then please inform your colleagues, and I don't want to create any difficulties. I am trying to help you only to improve your knowledge. Okay. Okay, then thank you for you joining. See you then next week at 5:30. Okay.
Thank you for your time, sir.
Okay, you're welcome. Bye bye.
Thank you. Bye.
Bye bye.
Bye.
Bye bye.